Okay, this will be a 1998 question 6, and this will be the first time this year we've done a full question 6. And question 6, they count for more points than any other problem of the AP exam, and they are typically the longest. Now, sometimes they're very confusing. This one's a little bit more straightforward. This is from 1998, and like I said, it is an investigative task, and it's a little bit longer. So the manager of a cultured pearl firm has received a special order for 2 pearls between 7 and 9 millimeters in diameter. From past experience, the manager knows that the pearls found in this oyster bed have diameters that are normally distributed. That's really important because we can't do things with the normal unless we know they're normal. So here they tell us they are, with a mean of 8 millimeters and a standard deviation of 2 millimeters. Assume that every oyster contains 1 pearl. The manager wants to know how many oysters he should expect to open to find 2 pearls. So they're looking for 2 pearls of the appropriate size for this special order. Complete the following parts to design a simulation to answer the question. All right. So to determine the probability of finding a pearl, well, notice when I say a pearl, although we're looking for 2, the problem talks about 2 right here. We're saying a pearl, so this is 1. And they've told us the mean for pearls was 8 inches and the standard deviation is 2. And they told us they're normally distributed. And they want us to know find the probability of finding one of appropriate size. Well, one of appropriate size means we have a mean of 8. And we're looking between 7 and 9. They also tell us, which is a little bit odd, they ask us to round our probability to the nearest 10th. So anytime they tell us normal, I go ahead and write z equals x minus mu over sigma and start plugging in. I also draw a picture. Well, this is the mean is 8, and the standard deviation they tell us is 2. They want it between 7 and 9. So I'm looking for this shaded area. So my probabilities, I want this x to be between 7 and 9. So I'm going to set this up as, I'll always take the larger one first. So the probability z is less than 9 minus 8 over 2, minus the probability that z is less than 7 minus 8 over 2, gives me, and this gives me the z-score of 0.5, and this gives me a z-score of negative 0.5. It is really important for grading purposes that you give those z-scores. College Board will count you down a half if you don't. So please go ahead and make sure you have those z-scores. Okay, so at this point, you actually have 2 different ways, well, multiple ways, and I'm going to go through 2 different ways right here on how to approach it on the calculator. So on the calculator, I can actually use the actual values. So on and second bars, normal, CDF, and we have a lower bound of 7, which is what we said, an upper bound of 9, a mean of 8, and a standard deviation of 2. When we do that, we end up getting a 0.3829. So the probability equals 0.3829, and they want us to round to the nearest 10th, which is 0.4. So that's one way to have done it. And the other way is go, hey, you know what? It's a z-score, and my z-score is actually going from -5 or negative 0.5 to positive 0.5 with a mean of 0 and a standard deviation of 1. So making sure that you understand that you can still use it just a plain old z-score. You know, second bars, normal, CDF, lower bound, negative 0.5, upper bound of positive 0.5, mean is 0, and standard deviation of 1. And if we did that, we'd still get the same 0.3829. So it doesn't really matter whether you went with z-scores or went with the actual values. You get 0.3829. This will suffice for work shown. Probability part A is 0.4. Part B, describe how you would use a table of random digits to carry out a simulation, determine the number of oysters needed to find 2 pearls of the appropriate size. Include a description of each. And then in this particular case, 0, 1, 2, 3, 4, 5, 6, 7, and 8 and 9 will represent what they'll represent in your simulation. Well, they told us here that they wanted that we're supposed to round to tenths of 40%. So somewhere it's like, okay, so 40%. So 0.4, and I have 10 digits, which means I need to choose 4 of those digits. Any 4 of those digits would represent pearls. The other 6 would not. And I've gone ahead and written this up so that it wouldn't have to wait for me to type it up. So I would assign 1, 2, 3, and 4 as oysters containing pearls of the appropriate size. I would assign 5, 8, and 0 as oysters that did not have pearls of appropriate size. This would say 5. I would assign 5 through 9. This is what that should have said. And 0 is pearls that did not have an appropriate size. I would work from left to right, allowing repeats. Why? We're working with percentages. Anytime we're working with percentages, I would allow repeats. I would do this until I had 2 pearls that represented oysters containing pearls of the appropriate diameter. And that would end the trial. I would then count the number of single-digit numbers that had been inspected, as that would represent the number of oysters necessary to have open in order to obtain 2 pearls of the correct diameter. I would repeat the process a bunch of times, numerous times, and take the average and average results from the trials. So that would be my explanation on how to do it. Next thing, it says perform that simulation 3 times. In other words, run 3 trials, and I assign 1 through 4 as oysters. Everything else is not oysters, or not pearls of not the right size. And then start at the upper leftmost digit and make your procedure clear so someone can follow what you did. All right, so here we go. So in this particular instance, and remember, repeats were permitted. So the very first pearl, the first oyster open, that's a success. 8 is not a success, 7 is not a success, but 4 is a success. So at this point, on the very first trial, trial number 1, I had to open 1, 2, 3, 4. So this is a correct, this is a wrong, this is a wrong, and that's a correct. So I had to open 4 oysters. Okay, I go to the next one, and I'm going to start it off on the next row just because it makes it easier. This is the wrong size. This is a correct. This is a wrong, a wrong, a wrong, and a correct. And on this particular one, I had to open 6 oysters. And over here, correct, wrong, 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 correct. All right. And so in this case, I had to open 7 oysters. So I had to open a total of 17 oysters. And by the way, they won't give you this table. I just had it, I made it up just to make it easy for us. And I take 17 and divide it by 3. And I find out that I need 5.667. I'm going to go back and circle my correct oysters. All right, so based on our simulation, we would expect to have to open an average of 5.67 oysters in order to find 2 pearls of the correct size. And by the way, I highlighted in green the ones that were the correct size, and the red is the wrong size. Okay, so that's part A, B, and C, and then we have part D. So the results of 2 100 trial simulations, one is for searching for 2 pearls between 7 and 9 millimeters, which is what we just conducted. And the other searching for 2 pearls between 4 and 6.5 millimeters are shown below. So we have 2, we have this distribution and we have this one. Now I'll notice that this one basically went all the way out to 14. And I'm not sure where the middle is, but somewhere probably around 4 and 5 is probably where the center is. This one, on the other hand, went all the way out to 29, and the mean looks like it's around the mean, or excuse me, the median is probably around 7, and the average is probably somewhere closer to 10, somewhere around there. We're not sure exactly where, because they're both skewed right. Okay, so please remember, so they're asking for, so at the very end, the question is, identify which distribution A, one that took less time, or B represents the search for 7 to 9 millimeter pearls, and explain your reasoning. Well, so there's a couple ways to approach this, and I'm going to use two different methods. One, I'm just going to use the normal and do that first. All right, so when I did the normal, we already calculated this one, and we found out that, hey, it was between, it was about 38%. That's the probability. And here, it was about 20%. So basically, when I ran this, if I run it from 4 to 6.5, and I didn't draw a picture of it, but if I had, it would have been centered again. We're centered on 8. We're sitting there between 4 and 6.5 versus the one that we had earlier, which was 7 and 9. Well, when I did this, and I did a second VARS normal CDF, I found out that it happened 0.2038. And just as a reminder, all you had to do was go to the calculator, second VARS, normal CDF, and I'm going to go ahead and use the actual values. And it says lower bound is 4, upper bound is 6.5, mean of 8, and standard deviation of 2. And we find out that that's 2.038. So I did that, and I actually wrote it down a second time just because for the second graph. Well, this one happened faster. Well, because this is a larger probability, I would expect that to be the one that happened faster. This is the one, because it's a smaller probability and less likely, I would expect it to happen, take longer to happen, or be less likely to happen. So I could have used that as my explanation, and that would have been a fine full credit answer. Is finding a pearl of 4 to 6.5 is less likely than finding a pearl of 7 to 9. We just showed that. We said finding a pearl of 7 to 9 was 38%. Finding it from 4 to 6.5 was 20%. And for that reason, an average would take longer to find. The distribution B is a simulation of 4 to 6.5, this one, because it took longer. And distribution A simulates finding a pearl from 7 to 9 because it took fewer trials. That would be an adequate and complete and total response. And I hope you could follow that. And basically all I did was sit there and run 2 normal CDFs, one for the 7 to 9, one for the 4 to 6.5. This one took less long, so it had to be distribution A. This one took longer, so it had to be distribution B. Now, the fact of the matter is, we are continuing to, basically, this type of problem says, hey, we're continuing until we have our first success. All right. And if we're continuing to that we have our first success, I could have looked as a geometric. Now, technically, this is a little bit more work to have done so, but I still want to do it because I think it's a very fair question and something that they could easily require us to do in the future. So I'm going to look at the same problem. And basically, there's our 7 and 9. I did the normal CDF, and I got the probability of being 0.3829 is the probability of getting one pearl of the correct size. Well, since if I look at this as a geometric, that would be 1 over p. So that tells me I would expect to find the first pearl in 2.61 tries. But I'm not looking for 1 pearl, I'm looking for 2 pearls. But as we combine random variables, we know that we can add those probabilities. And 2.61 plus 2.61 happens to be 5.22. So we would expect it to take 5.22 trials. Well, just looking at the graph, I can tell that, hey, it's not B, that must be A. But we also could sit there and go, you know, another good thing that we can do is we could take this expected value. It took us 9 trials out of 100. So this is 9 divided by 100, 22 divided by 100. So these are the, if I divide these all by 100, all the occurrences by 100, I end up with probabilities. So 2 times 0.09, at 3 times 0.22, at 4 times 0.20, 5 times 0.12. And I loaded that all into the calculator, and I found out that my simulation predicted it would take 5.166. My theoretical is 5.22, so not substantially different. So based on this, I would go, you know what, that looks like it's A. But I went ahead and tested B doing the same thing. Well, we found out that the probability that it would occur is 20%. All right, so 1 divided by 0.2039 is 4.9. Because this is my expected value of a geometric, 1 over P. However, that's the probability of finding the first pearl. We're not looking for 1 pearl, we're looking for 2 pearls. But we know that by combining random variables, we get 9.808 because we can add means. All right, we can add means directly. Standard deviations, we can't, we have to square them first. But means we can add directly. So I would expect it to take 9.8 to find 2. Once again, it was a simulation of 100 trials. So I can divide all these by 100. This happens 3% of the time, 6%, 7%, 8%, 13%. When I do that, I go ahead and calculate my expected value. And I get 2 times 0.03 plus 3 times 0.06 plus 4 times 0.07, all the way up to 29 times 0.01. So this would tell you that I would expect my simulation expected value is 9.36, which is not that far off of the theoretical. So this was the theoretical, this was what the simulation produced. So it's clear this 5, it's clear that the 4 to 7, I mean the 7 to 9 millimeter was associated with distribution A, simulation A, and the 4 to 6.5 was simulation B. So, and the reason I gave equals 5.6 is simulated expectation is closer to the predicted expectation for the number of trials. So basically, you could have done it this way, much longer, but I wanted you to see a couple things. 1, reminder of the expected value. 2, you can combine means or combine random variables. And this, because we're going on to the first, this makes it a geometric, and our probability was what we calculated with the norm. Okay? All right, hope you enjoyed the video. Thank you.